Our universe is a place of constant motion and change. From the smallest atoms to the largest galaxies, everything interacts through a delicate dance of forces. We experience these forces every day: the pull of gravity that keeps us grounded, the electromagnetic force that powers our homes, the strong force that binds atomic nuclei, and the weak force responsible for radioactive decay. These fundamental forces govern the cosmos, dictating how matter and energy interact and evolve. For centuries, physicists have sought to understand these forces, unraveling their secrets one by one. But what if these seemingly distinct forces were not so different after all? What if they were merely different facets of a single unified force that governed the universe from its earliest moments? This tantalizing possibility has driven physicists on a quest to unify the forces, a journey that has led us to the heart of the Big Bang and the very essence of the cosmos. This quest for unification is not merely an academic pursuit, it strikes at the core of our understanding of the universe and our place within it. By unifying the forces, we are not just simplifying our description of nature. We are uncovering a deeper, more profound truth about the fundamental building blocks of reality. The desire to unify seemingly disparate phenomena is a recurring theme in the history of science. In the 19th century, James Clerk Maxwell achieved a landmark unification by demonstrating that electricity and magnetism were not separate entities, but rather two sides of the same coin, electromagnetism. This triumph paved the way for a new era of physics, one that sought to unify all forces under a single theoretical framework. Inspired by Maxwell's success, physicists set their sights on a more ambitious goal: unifying the electromagnetic force with the weak nuclear force responsible for radioactive decay. At first glance, these forces seemed worlds apart. Electromagnetism, with its infinite range, governs the interactions of charged particles and gives rise to light itself. In contrast, the weak force operates at minuscule distances, mediating interactions within atomic nuclei. Despite these apparent differences, a few tantalizing clues hinted at a deeper connection. Both forces involved particles with spin, a fundamental quantum property, and their strengths, while vastly different at everyday energies, seemed to converge at extraordinarily high energies. This convergence suggested that perhaps at some fundamental level, these forces were one and the same. The breakthrough came in the 1960s with the development of the electroweak theory, a triumph of modern physics. Independently proposed by Sheldon Glashow, Abdus Salam, and Steven Weinberg, this theory unified the electromagnetic and weak forces into a single, elegant framework. According to the electroweak theory, at extremely high energies, such as those present in the early universe, these two forces were indistinguishable, existing as a single, electroweak force. As the universe expanded and cooled following the Big Bang, this unified force underwent a process called spontaneous symmetry breaking. This process, akin to water freezing into ice, caused the electroweak force to split into the distinct electromagnetic and weak forces we observe today. The electroweak theory didn't just unify these forces, it predicted the existence of new particles, the W and Z bosons, responsible for mediating the weak force. The experimental confirmation of these predictions came in the 1980s with the discovery of the W and Z bosons at CERN, validating the electroweak theory and earning Glashow, Salam, and Weinberg the Nobel Prize in Physics in 1979. This triumph marked a pivotal moment in our understanding of the universe, demonstrating that seemingly disparate forces could indeed be unified under the right conditions. The unification of the electromagnetic and weak forces was not just a theoretical curiosity, it provided profound insights into the conditions of the early universe. Just moments after the Big Bang, the universe was an unimaginably hot and dense soup of energy, where the electroweak force reigned supreme. As the universe expanded and cooled, the electroweak force split, leaving behind a faint echo of its unified past. By studying the properties of the weak force and its interactions with matter, physicists can probe the conditions of the early universe, piecing together the events that unfolded in the first fraction of a second after the Big Bang. The success of the electroweak theory has fueled the quest to unify the remaining forces, seeking a single framework that encompasses all of nature's fundamental interactions. Section 5. Guts. A step closer to the Holy Grail. Emboldened by the success of the electroweak theory, physicists set their sights on an even grander unification, combining the electroweak force with the strong nuclear force, responsible for binding quarks within protons and neutrons. These grand unified theories, or GUTS, propose that at even higher energies, the electroweak and strong forces would merge into a single, unified force. While GUTS remain theoretical, they offer tantalizing glimpses into the nature of the universe at its most fundamental level. These theories predict a variety of exotic phenomena, including the decay of protons, the existence of magnetic monopoles, particles with only one magnetic pole, and the properties of neutrinos, elusive particles that rarely interact with matter. While experimental evidence for GUTS remains elusive, the search continues. Physicists are constantly pushing the boundaries of experimental techniques, hoping to find telltale signs of these unified forces at work in the cosmos. Section 6. The Elusive Theory of Everything. The ultimate goal in the quest for unification is a theory of everything, a single, elegant framework that encompasses all four fundamental forces including gravity. Such a theory would be the holy grail of physics, providing a complete and consistent description of the universe from the smallest subatomic particles to the largest cosmic structures. While a complete TOE remains elusive, several promising candidates have emerged, including string theory and loop quantum gravity. These theories, though still in their infancy, offer radical new perspectives on the nature of space, time, and gravity, suggesting that our current understanding of these concepts may be incomplete. The development of a TOE would be a monumental achievement, representing the culmination of centuries of scientific inquiry. It would not only revolutionize our understanding of the universe but also raise profound philosophical questions about the nature of reality itself. Section 7. Unification and the Big Questions. The quest to unify the forces is not just about finding a single equation that describes everything. It's about answering some of the biggest questions we can ask about the universe. Why are there four fundamental forces? What happened in the first moments after the Big Bang? What is the ultimate fate of the universe? By understanding how the forces were unified in the early universe, we can gain insights into the processes that shaped the cosmos into what we see today. Furthermore, a unified theory could shed light on the nature of dark matter and dark energy, mysterious entities that make up the vast majority of the universe's mass and energy, but remain shrouded in mystery. Section 8. The journey continues. The quest to unify the forces is a journey that has taken us from the smallest subatomic particles to the vast expanse of the cosmos. While a complete theory of everything remains elusive, each step towards unification brings us closer to understanding the fundamental nature of the universe and our place within it. The journey is far from over. New discoveries and technological advancements continue to push the boundaries of our knowledge. As we delve deeper into the mysteries of the universe, we can be sure that the quest for unification will continue to inspire and challenge us, driving us towards a deeper understanding of the cosmos and the fundamental laws that govern it.